So I first fix a setup. So K is a compact Lie group, and I also use G as its amplification. So this is a gauge group, and I choose M. It's a quaternionic representation of K, and that is called hypermultiplet in physics literature. And later, I assume that M is of cotangent type, which means M is a direct sum of N and J times N. J is an element in the cotanine. And N is a usual complex representation. And if you have pairs of K and M, then you can consider the 3D N equal 4 supersymmetric gauge theory. And you can also consider 4-dimensional N equal 2 supersymmetric gauge theory. But I first mainly focus on 3D case. And then you can define Higgs branch and Coulomb branches. So as a mathematician, Higgs branch is easier to understand. This is just a hyperkähler quotient of M by K. So I use this notation. And the Coulomb branch is more difficult. So it is classically of this form, R3 times S1 to the power rank K divided by Y. But it receives a quantum correction. And after quantum correction, the Coulomb branch is not this classical description, and it is difficult to understand. So, but starting from the work of Sarkar-Mitten, so there are many cases determined for pairs of many cases of pairs K and M, the Coulomb branch has been determined. But somehow, because this quantum correction doesn't make sense to mathematicians, so it took 18 years to find a mathematical definition of Coulomb branch. So this was found some years ago by myself and subsequent work with Finkenberg and Weberman and Finkenberg. So that I'd like to explain. So Coulomb branch is expected with hyperkähler manifold, possibly with singularities, but we defined Coulomb branch as a holomorphic symplectic variety. So in particular, I don't know how to construct hyperkähler metric, but at least I can define complex structure and holomorphic symplectic. And this definition was given, as I said, my joint work with Weberman in 2018, for the assumption that the M is a cotangent type. And then later, it was extended to more general case, but with certain necessary condition for the anomaly cancellation condition. So by these people, Weberman, Degron, Finkenberg, Raskin, Flavin, and independently by Taylor. Today, so as I said, I will focus on the cotangent type case. And so anyway, so this more general case is based on the cotangent construction for the cotangent type. So I think it is more basic to understand the definition of cotangent type case. So idea is roughly stated as follows. So in order to define, maybe I should also say this, Coulomb branch is not only holomorphic. This is affine variety. Affine variety means that it is defined as an algebraic equation by inside the affine space. So then for such variety, it is enough to define its coordinate, the ring of polynomial functions on this variety. So you just need to define a commutative ring. Then there's the so-called spectrum constant. So you just consider it's the space of maximal ideals of this commutative ring. Then you recover the space. So this is called spec in mathematics. So it is enough to define the commutative ring. And this commutative ring is nothing but the quantum Hilbert space of the gauge theory associated with S2. And this S2, quantum Hilbert space of S2, is a ring of dressed monopole operators proposed by this physicist in a long time ago. So if you can make sense of monopole operators, then you can consider its ring, and then you just take a spectrum to define a Coulomb. But there is one slight technical problem. Yeah, basically we follow this line of argument, but there's a little delicate point. So the monopole operators, as I will explain later, are difficult to define. But nevertheless, the ring generated by them can be defined. So there's slight difference between the ring and its element. So monopole operator is an element in the ring. So as I said, it is a little difficult to define monopole operators themselves. But the ring, at least we can define the ring. So this is what I want to explain. And the ring is defined by using standard technique in geometric representations. Okay. So this part might be a little bit a difficult part for physicists, but I tried. So anyways, if you have any question, please stop me and ask a question. I first give you our definition, and then I try to explain its connection to physics later. So anyway, we use the so-called affine Grassmannian. So affine Grassmannian is a infinite dimensional homogeneous space, denoted in this way. So G of Z. So this is a formal Roland power series with values in G, the complexification of the gauge group, divided by formal polynomial ring with values in G. So this is an analog of the partial Flag variety in finite dimensional case, but the group which acting on on affine Grassmannian is infinite dimensional space. So this infinite dimensional Katsumudi group acts on the affine, and it is homogeneous. And then I took the smaller group action. So this is the group which you take the quotient, but I consider the action of this group from given by the multiplication from the left. So this is some non-trivial action, and you see that the orbit, you have the orbit space decomposition, and orbit is parameterized by dominant coordinate. So this is very similar to the Schubert cell decomposition of the Flag variety in finite dimensional case. So if you consider the Flag variety in finite dimension, and if you consider the orbit by Borel subgroup, then orbits are parameterized by Weil group. And if you slightly more generally, so if you consider partial Flag variety, then it is a coset of the quotient for the full Weil group by the partial Weil group corresponding to parabolic subgroup. And if for the affine Grassmannian case, this is an affine Weil group, coset of affine Weil group divided by finite Weil group. And you have the lattice of weights, or more precisely, co-weights in this case. Further, the quotient out by the action of finite. So you get a dominant coordinate. So I will use this decomposition later, and it will be important to make connection with the physics literature. So this is the very roughly, this is the how to say it, gauge theory on small two-dimensional disk, and so because we are considering the gauge theory associated with the group G and the representation N, so I consider some also add the space of sections of the associated bundle. This is done by this way. So I consider the space T, TGN. So this is an infinite rank vector bundle order 5 plus Riemannian. So I should, so this is notations. So this is formal power series. And this is formal power series, and this is formal Coulomb power series. Okay. The fiber is this one. So n valued formal power series. So this means that you consider the n valued function on the disk, small disk, 2-dimensional. Then I slightly change the space in the following way. So RGN, so this is the main player. This is the intersection of fiber product of TGN and N of G over N of G. So T of GN, so you have the, so you have a N valued formal power series, and you change by this group element. Then because this element could have pole at, this is a formal Coulomb power series, so you could have negative powers. So if you multiply the element, then the result could have the negative power. So it has values in formal Coulomb power series. But you restrict the subset of TGN such that those elements has no negative power. So this is RGN. So maybe this is secretly you consider the 3-dimensional gauge theory, but the time direction is infinitely small. So I have disk. So this is a small disk, and they have small another disk glued along the punctual disk. So this is D minus origin. So I have section S of Z, N of Z in upper disk, and lower disk we have GZ times S of Z. G of Z is a gauge transformation between the upper disk and the lower disk. So, but I remove the origin, so G of Z could have negative powers in Z. So in particular, if we multiply G of Z SZ, then it could have poles. But so this should be a well-defined element in the lower half of the disk. That then I require G of Z should not contain negative power. So this is the meaning of RGN. So RGN is a configuration gauge theory on this how to say some toy model for the 3-dimensional manifold, which is given by this gluing of 2 disks. And this is some cartoon for the S2. So that's the reason why if you consider this moduli space, you can define the quantum Hilbert space for S2. So anyway, so this H of S2 is defined as the so-called equivalent of homology of this parity RGN. So by the way, so this parity RGN is called parity of triples. And you can define the convolution product. So basically, the convolution product, you consider this diagram, and you add one more disk like this. And then from here, from upper part, you recover this, and for the second one, you recover this one. But you can also forget the middle disk. Then you recover this one. So you have 3 ways of project from here to here. And then you pull back. So if you have a homology class here, and then you pull back by 2 ways, here upper part and the lower part. And then product means that you just restrict the top and bottom and push further to this original. So this is the conversion. And the degree must be properly defined. So in particular, this is a graded ring, but not positively graded as usual for the homology group. So the degree could be both positive and negative. And four-dimensional case, which I mentioned at the beginning, so you just replace the homology group by K group. So this, on the RGN, you consider the coherent sheaves, and you consider the corresponding Grothendieck group. So this is the definition for the four-dimensional Coulomb branch. And in comparison with the previous talk by Mansion, so this is first of all, so we are considering not on R4, but we are considering the case on R3 cross S1, and instead of so in that case, the Coulomb branch is something like a Hitchin modular space. And for R4, the Coulomb branch is the base of the Hitchin modular space. But as it's known that the Hitchin modular space has a hyperkähler structure. And in this definition, so I just take again, I take the spectrum of this commutative ring. So this gives the complex structure, which Mansion didn't use at all. So he talked about the Seiberg-Witten curves, and so this Seiberg-Witten curves is a spectral curve for the Hitchin integrable system. But the Hitchin integrable system is defined in another complex structure, which I cannot, which is different from the one which I described here. Okay. But nevertheless, so it is expected that this complex structure and another complex structure can be extended to the hyperkähler structure on the modular space. And because of this reason, so in four-dimensional case, you only consider the superconformal case or asymptotically free case. So that means the representation N cannot be too big compared with the group G. For example, if N is a copy of direct sum of copies of fundamental representation for SU2, then you can consider up to four fundamental matters. But for this construction, we don't have such constraint. So anyway, so we define in this way. And from this construction, we can also construct a deformation quantization of a Coulomb branch. So this is just given by considering the C star action on the whole picture. So Z, as I said, maybe I didn't say properly. So this Z is a coordinate for the disk. So you can rotate the disk. So this is an action, Z maps to T times Z. And because all the construction can be made C-star equivalent, so you can define a C-star equivalent homology group or a C-star equivalent K group. So then, maybe I didn't say properly. This is a commutative. This ring is commutative. But once you put the C-star action, then it is no longer commutative. So it is a non-commutative deformation of a commutative, so which is nothing but the deformation quantization of the spectrum of this commutative. And once you have the deformation quantization, then you can define the Poisson bracket on the original commutative ring by the usual formula. So if you have function and f and g, its Poisson bracket is defined in the following manner. You first lift to the non-commutative deformation and take commutative data, and then divide by h bar. This h bar is the generator of system. Okay. and take H by. So the leading part of the commutator is Poisson bracket. And you can show that this Poisson bracket is coming from the symplectic structure. Okay. And the classical Coulomb branch, which is in fact the Coulomb branch before quantum correction, it can be recovered in the following way. So maybe I should emphasize that in this definition, the quantum corrected Coulomb branch is defined in this manner. And then by analyzing the quantum corrected Coulomb branch, I can recover classical Coulomb branch. So in that sense, this is somehow different from the usual way physicists understand. So let T be a maximal torus of G. And I restrict the representation N to T. So then it is another pair of the group and hypermultiplet. So you can consider the corresponding gauge. This is abelian gauge. Then in terms of this construction, so I can consider variety of triple for G and N, but you can also consider the variety of triples to T and N. And also you can consider the variety of triples to the zero representation. So this is R and T and zero representation, zero dimensional representation. Then because we don't consider any section, it's just you just consider pure gauge. So in this case, the gauge group is torus. So this is just a variety of triple becomes just affine plus phi. And this is some discrete space. So this is the space of co-character. So for this space, you can just compute this definition. And so this equivalent homology group. And then you easily find that its spectrum is a real algebra of T times dual torus. So this T comes from because we are considering the equivalent homology group. And T check appears this space of co-character can be regarded as the space of characters for T check. So T check is dual. Then the original ring, commutative ring, this is the space of functions of the coordinate ring. And this ring is related by the natural homomorphism between those, the induced from the natural homomorphism on the homology groups induced from the inclusion of the spaces. So variety of triple for the abelian gauge group is a sub-variety in the original variety of triples, and I denote the inclusion by iota. And because we just consider the case when the section vanishes, so we have the also inclusion, which I denote by Z. Then I have push-forward homomorphism. And there's slight complexity because for here I consider the equivalent homology for T, and here equivalent homology, the coefficient group is G. So because of this, I need to take the wire group invariant part. And also here. And for the second relations, I take the pullback with respect to G. And then because of W, we take the W invariant part of this space of functions. And this is a Coulomb branch, coordinating Coulomb branch. And this homomorphism induced from the equivalent homology group have nice properties because of the localization theorem in the equivalent homology group. So it says that, so this is a very standard fact. So this homomorphism, iota star and Z of star, become isomorphism if I tensored with the coordinate coefficient ring to its quotient field. Quotient field of equivalent homology torus. So in practice, this tensoring the fraction.
Excuse me.
Yes.
Yeah, well, what is the P? T cross P.
T cross P.
P dual.
Not T. I'm sorry. This is T. I don't use T. P.
No, P.
Sorry,
P.
my letter is not good. T cross T check.
T check. Okay.
T check is dual torus. Okay, so this is also T. Is it clear? So in the equivalent, so this is a homomorphism between the equivalent homology groups. So those are different spaces. But if you tensor with all the modules of equivalent homology point, and if you tensor with fractional fields of the equivalent homology torus, then all becomes isomorphism. So in the space, in the spectrum, in the level of spectrum, it means that the Coulomb branch is birational to T cross T check divided by Y group. So the Y group invariant taking Y group invariant means that the quotient by Y group. So this is a birational. So in this way, we recover the classical Coulomb branch from in our definition. Okay. So I'd like to explain how we can recover the so-called monopole formula from this construction. So as I said, affine Grassmannian has a Schubert decomposition. So then maybe I didn't say. So because of this definition, TGN is a vector bundle over the affine Grassmannian. So you have the corresponding decomposition, and you have the induced corresponding decomposition of RGN. So this is what I mean by this RGN lambda. So then RGN lambda is mapped to this Schubert cell, and it is also well known that this Schubert cell is a vector bundle over this partial Flag variety G mod P lambda. P lambda is a parabolic subgroup which contains a stabilizer of the lambda. So anyway, from this, and also you can show that this first projection is a vector bundle. The second vector, as I said, second projection is well known to be vector. Then the homology group of this piece is isomorphic to the homology of this base space by Thom isomorphism. So vector space has trivial homology group. So because of that, you get this isomorphism. And then we are considering this homogeneous space and take equivalent homology with respect to the group acting on this space. Then again, by well-known result in the equivalent homology, this is the equivalent homology point. And it is also known that this is equivalent. This is just a polynomial. And we understand this piece as the approximation of the monopole operator. But as I said, there's a difficulty to understand, to define the monopole operator rigorously. So, and this is the point which I want to explain. So the space RGN decomposed into pieces, and each piece is RG n lambda. There is a homology group, I understand, as like this. So it is parameterized by lambda and also element in polynomial in this operator. So in this sense, so if you consider non-trivial polynomial, this is called dressed monopole operator. And the difficulty is that although the space is decomposed into pieces, if you take the homology group, then the homology group is not the direct sum of each piece. So this is a difficult point. But what we can actually show that, so this left-hand side, this is a ring, and this has a filtration, and whose associated graded is this right-hand side. So, and each graded piece is given this sum. Okay. So we have, so left-hand side is F0 and F1. Maybe better to. So this index is in fact indexed by 4 characters, so it's not proper. But anyway, so we have this kind of filtration, and associated graded is F0 divided F1 plus F1 divided F2 plus and so on. So in order to make isomorphism between the original left-hand side and the right-hand side, somehow you need to take a complementary subspace. So F1 is a subspace in F0, for example. So in order to write F0 as a direct sum of F1 and plus F0 divided by F1, you need to identify quotient space F0 divided by F1 as a subspace. So you need to take a complementary subspace to F1. But I don't know how to do it canonically. So in that sense, so the monopole, in order to define the monopole operator rigorously, then somehow I need to identify F0, the identity to define a complementary take a complementary subspace to F1, so that I can consider F0 and quotient space F0 divided by F1 as a subspace in F0. So as I said, this I don't know how to do. But anyway, so in order so the monopole formula just to compute the dimensions of this space, or more precisely graded dimensions. There's natural grading over here, and monopole formula computes a graded dimension. So for that purpose, so this program of the filtration and complementary subspace disappears. So the graded dimensions are the same for the left-hand side and right-hand side. And the dimensions of each pieces you can easily compute. And then you recover the monopole formula proved by Coulomb-Rice, Hanani, and Zafarov. Okay. So they obtain the monopole formula counting monopole operators, but because of this reason, so we don't know how to justify what actually they mean by monopole operators. So let us look at a little bit more precisely the structure of these pieces and how they glued if I change lambdas. So the Affine-Grassmannian, as I said, Affine-Grassmannian has this decomposition, and it looks like Schubert cell decomposition. And for Schubert cell decomposition, you can consider the closure of Schubert cell, which is Schubert varieties. So this is a singular variety, so it is usually difficult to analyze, but you can still consider the its how to say its structure. So I define the Schubert variety GRU-G of lambda as union of GRU-mu, where mu runs smaller than or equal to lambda. So the open part of this Schubert variety is GRU-G lambda, but it contains also smaller GRU-G. Then in order to look at how GRU-G lambda and GRU-G mu are glued together, so there's an observation by Breber and Finkel. Maybe this go back earlier probably, but I find this statement in Coulomb paper in 2010. So they computed the slices, which mean that locally, so affine Grassmannian Schubert varieties look like along this smaller Schubert cell, look like product of G mu times this variety, W bar lambda mu. So this W bar lambda mu is a moduli space of singular monopoles, or it's equivalently S1 equivalent instant on zone R4. So you have the S1 acts on R4 as usual. So R4 is the identified with C2 and it's S1 acts by multiplication by T for the first component, T inverse for the second component. And then you need to pick up a boundary condition, which is monodromy at the origin, the fixed point of this action, and also at infinity. And this lambda and mu appears is this monodromy at 0 and infinity. Okay, so this is a familiar space in Gauss. And for example, if the group G is type A, or even for classical groups, so this singular monopole moduli space have ADH description. And for example, if G is a type A, then W bar lambda mu is what people call the quiver variety of type A. So anyway, so you have various ways to understand W bar lambda. So as an application, for example, you can say the following. So if lambda is minuscule, so minuscule means that lambda is a minimum element with respect to this ordering. So maybe I didn't say, so this is not the total order. So you could have identity is a minimum element, but you could have other minimum. For example, if you consider the when G is GLN, then fundamental forward is minimum. So anyway, so there is notion called minuscule. So in this case, because there is no smaller Schubert cell, the closure is equal to the orbit itself. Closure is the cell itself. And in this case, because we need to add the smaller pieces, it's easy to understand the homology group of this closure. So this is nothing but these pieces, which, as I said, this is something to understand. So in particular, for example, so you can compute the fundamental group, fundamental cycle, and you compute by this way, like this. So yes, using the localization theorem. So if you have an element in here, so you can by isomorphism, which you allow the fractional polynomial, then you get the element in here. So you get something, this is explicit. So you have the explicit formula. So this is something like this. So it's a sum over lambda prime, which is the wild group orbit in the lambda, and you consider the corresponding lambda prime is a co-character, so you consider as an element point in the affine Grassmannian for the torus, and you consider its fundamental class. And then you get some fraction in equivalent variables. And then in the denominator, you have the equivalent Euler class of the tangents to space at the affine Grassmannian. And then in the numerator, you get some expression, the basically equivalent Euler class of the bundle which correspond to the representation. So I don't write on the very explicit one, but this is very, it's very, very explicit. So in this way, you at least for when lambda is minuscule, we can write down the corresponding monopole operator in this way. And also you can see the what physicists called monopole bubbling. So that means this part. So this singular monopole, W bar lambda mu. So this space itself possibly could have singularity. So as I said, the problem is how to say. So this guru lambda G is difficult to understand, difficult to analyze because of singularities. And this singularity is reflected to the singularities of double bar lambda mu, and the singularities of this double bar lambda mu is related to the so-called monopole bubbling. So roughly it says, so if you consider group lambda G bar, so, and if mu is smaller than lambda, smaller or equal to lambda, then group G mu closure is contained in here. But if you take the mu smaller than mu, then corresponding Schubert cell could be contained in this middle Schubert variety. And this smaller piece is the source of the singularity of this singular monopole modular space. But nevertheless, because of this structure, you can try to define the monopole operator in the following way. So you first take the contribution from the orbit. So this is the contribution which you already see the case of the monopole, minuscule monopole operators. So this is expressed expression, and this makes sense for any lambda, not necessarily minuscule. So you can write down the corresponding operator. So this is the main contribution to the monopole operator, candidate of a monopole operator. But then, because of this structure, you should add smaller contribution, and that is given by the following, this kind of expression. So the first term is again sum over the wire group orbit, and the first term, so this rational function is the same as the case of this coefficient, monopole, the same as a minuscule monopole operator. And again, this is a contribution equivalent Euler class for the some bundle associated with n divided by the equivalent Euler class of the tangent space. But because you have this singular monopole contribution, so you should correct with some equivalent cohomology class, integration of equivalent cohomology class over the singular modular space. So this in this way, so people expected to have to define the monopole operator more rigorously. And in fact, this kind of expression appears in physics literature. So it took the Taki first, and they and also Hayashi Okuda, Yoshida and Okuda Yoshida, and other works of Yoshida and collaborators. But here there is the subtle point. So as I said, this double bar lambda mu, so this is a monopole modular space. So this could have singularities. So then, and the equivalent cohomology class. So this is some equivalent Euler class of vector bundle over the singular modular space. But this vector bundle is usually defined only on the smooth locus of the monopole modular space. So you must extend this cohomology class to the whole space, which could have singularities. So this is in general difficult. So those physicists use the following strategy. So they usually assume the group to be GLN. Then in this case, rather happily, so this singular monopole modular space have resolution. And this resolution is parameterized by mu and lambda, but lambda is now a vector. So lambda is a tuple of co-weights whose sum is equal to lambda. And in particular, if lambda I is minuscule weight, then this corresponding space becomes smooth. And for G equals GLN, we have lots of minuscule weight. Because of this reason, we can take a resolution in this way. And the difficulty is that if G is not GLN, then we don't have much minuscule weight, co-weight, and in general, you cannot construct a resolution in this way. But anyway, so they assume D is GLN. Then they make sense of this integral, equivalent integral. This is very similar to the necklace of partition function for instantons on R4. So instead of R4, they consider the S1 equivalent instanton. So, but still the necklace partition function can be defined very similar. But now the pay applies that. So this resolution of singularity depends on the ordering. So this, as I said, lambda vector is the tuple of co-weights. And this depends on the ordering in general. So this is a subtle point. So this expression depends on the ordering of lambda 1 to the lambda n. And so somehow they must pick up the non-dependent expression. And this is the most difficult point. And this ordering also compatible with the deformation quantization of the Coulomb branch, which I mentioned. So if I once turn on the equivalent variable, she starts acting on the disk, then the resulted ring is no longer commutative. So in particular, the product depends on the ordering. So this ordering corresponds to this ordering. So in that sense, this dependence is natural in view of the non-commutative deformation. And in some sense, I mean, in order to understand the appropriate mathematical definition of monopolar, so you should have some appropriate understanding of this non-commutative deformation. And I also want to mention our result, which is a little bit more general in the sense of group, but more restrictive in the sense of the representation. So if G is general and N is either zero-dimensional representation or adjoint representation, then we can take a resolution singularities. But here, this resolution is hyperkähler manifold, and in here, this space is no longer hyperkähler. So it is some degenerate in the symplectic structure. It's degenerate here. But anyway, so you have you can construct some explicit resolution. Then you can compute the contribution for the smaller cohort. And this is useful for the adjoint representation to understand the deformation quantization. So in this case, deformation quantization is spherical part of the double Hecke algebra of Cherednik. And in that case, so this expression is correspond to the MacDonald operator, or its degenerate version. And people have noticed this kind of expression of first main part, which is just MacDonald operator in type A, but in other types you needed to correct it by some smaller terms. And we can recover such expression in considering the resolution. So anyway, so this is I'd like to emphasize that this definition of the correction term to this main part is a difficult, delicate problem. And then finally, I'd like to mention recent development in this problem. So this is this is discussed in recent preprint by Curtis and Williams. So they consider the four-dimensional case, not the three-dimensional case. So as I said, in the four-dimensional case, so the Coulomb branch is defined by K-glutamic group of the coherent sheaf on this variety of triples. But so this glutamic group of coherent sheaves is isomorphic glutamic group of the derived category of coherent sheaves. So we can consider this way. Then Curtis and Williams introduced the non-standard T structure on the derived category. So this is a little difficult part of the difficult mathematics, but maybe you heard about the homological mirror symmetry, which is formulated as a equivalence between the derived category for coherent sheaves on Calabi-Yau and derived category for the Fukaya category for the mirror. And so this is a really equivalence between the derived categories. And if you just consider the coherent sheaves, it doesn't really correspond to anything to the Lagrangian in the Fukaya side, Fukaya category side. So in terms, so in order to understand the Lagrangian submanifold in the original side, Calabi-Yau side, so you original Calabi-Yau side, then you somehow need to introduce the so-called T structure. So anyway, so there's some machinery which has been studied in mathematical literature. Then there's once you have the T structure, then you can consider its hard. So this is an abelian category. So in general it is not true, but maybe very roughly. So if you start this abelian category and if you consider its complex and define the derived category in the usual way, so then it is something close to the original derived category. So anyway, Curtis and Williams proved that this hard is a monoidal abelian category. So this abelian category is different from the abelian category of coherent sheaves. And then they defined the canonical basis of this four-dimensional Coulomb branch as class of simple object in abelian category. So this is the so-called finite length abelian category, and you have base of its glutading by its simple object. So this is not coherent sheaf. This is still the complex of coherent sheaves. So it's a difficult object, but by this kind of abstract categorical approaches, you can consider it simple object. Then so the proposal of the Curtis Williams is that this is the mathematical definition of the monoproprietary, or more precisely that operator, because they are considering four-dimensional two theory. So this class is an element. Finally, we get the element in this being. So in this way, we have the element in here, not the element in this associated grade like this. Like, okay, we will get the element, canonical element. Then there are lots of open questions on this construction. So for example, so then is it possible to recover this kind of expression? I believe this is more or less possible, but then so this part is given somewhat abstract manner and concrete complication, expressed determination of this expression for this canonical basis element might be difficult for me in general, but at least in some small cases maybe they can. I hope this could be done. And also more interesting question is that it is expected this construction is compatible with the expected cluster structure on this four-dimensional Coulomb. So this commutative ring is expected to be having cluster structure, And then once you have the cluster structure, you have a notion of cluster monomial. This canonical basis contains the cluster monomial. So that is what I mean by compatibility. So if I think this cluster structure has been explored in view of this realization of Coulomb branch as the character variety, and so as I said, this is something similar to the Hitchin moduli space, and in the generic complex structure, it is close to the character varieties, and so many people have been studied the cluster structure on the character varieties, and so this more generally, so we expected this four-dimensional Coulomb branches as cluster structures, and further, this canonical basis contains the so-called cluster. Okay, that is. Thank you very much for attention. Nice talking.